Hello, good day everyone. My name is Sivarama. I'm going to present today about introduction to photonics. The course outline for today, I'll start with the introduction and then proceed with the ray optics, where we will be looking at the law of refraction, also known as Snell's law, and we will be looking into fiber optics as well its associated components. Right? And then we move to wave optic. In wave optic, we will be looking into wave equation, monochromatic wave, law of reflection, refraction, diffraction, as well interference and interferometer. Right? And then we will proceed with the electromagnetic optics, where we will be reviewing the theory of light, wave equation, TEM, and also polarization. Okay. And then the last topic will be on quantum optics, where we will look into photons, absorption, emission, fluorescence, as well photon sources and photo detector and modulator. Okay, on the introduction, let's look into the inventors, right? Start with Newton. He has already set forth a theory of optics that stated light emission consists of collection of corpuscles that propagate rectilinearly, right? And Fermat, he has enunciated a rule known as Fermat's principle. Light ray travel along the path of least time relative to neighboring path. Okay, and also mentioned that light travel in a straight line. All right. Light can be described as an electromagnetic wave, and this conception is called electromagnetic optics. Okay, electromagnetic radiation propagate in the form of two mutually coupled vector waves, namely electric field wave and magnetic field wave. The optical phenomena can be described using simplified scalar wave theory by a single scalar wave function, and this is called a scalar wave optic or wave optic. Right? When the light wave propagates through and around objects whose dimensions are much greater than the wavelength of the light, the wave nature is not readily discerned, and the behavior of light can be described by rays. Right? So this model of light is called ray optics. So let's look into the figure 1.0, right, where we have it start from the ray optic and then evolve to wave optic and evolve to electromagnetic optic, and then now we are in quantum optics, right? So what this picture illustrates, basically the wave optic is encompasses of ray optics, and also electromagnetic optic encompasses wave as well ray, and quantum optic encompasses all the three. Okay. So electromagnetic optic encompasses wave optics, which in turn encompasses of ray optic. And electromagnetic optic provided the most complete treatment of light that confined to classical optics. Right? However, certain optical phenomena are characteristically quantum mechanical in nature that cannot be explained classically. Example like absorption, emission, photoelectric effect. Okay? And these phenomena are described by quantum version of electromagnetic theory, also known as quantum electrodynamics, and this is referred as quantum optics. The theory of quantum optics provides an explanation for virtually all optical phenomena. Quantum electromagnetic theory or quantum electrodynamic QED or quantum optics accepted as a theory that is useful for explaining almost all known optical phenomena. Right. Let's start with the ray optic. Right, ray optic, the light wave propagate through and around objects whose dimension are much greater than the wavelength of the light. Right, and as defined by Newton and Fermat, light travel in straight line. Right, the behavior of light can be adequately described by ray obeying a set of geometrical rules. In mathematical perspective, ray optic is the limit of wave optics when the wavelength is small. the simplest ray optic is the simplest theory of light, right? Light can be described by rays that travel in different optical media in accordance with a set of geometrical rules. Right? And ray optics is also called as a geometrical optics, right? And ray optic concerned with the location and direction of light rays. Okay, this phenomena is useful in image formation and collection of rays from each point to an object and their redirection by an optical component. And this can be illustrated in the picture below. Okay, on the left hand side, that the object ray is being reflected to the human eye, right, through the mirror. And at the same time, we can look also that the rays appear to be being transmitted from the virtual image, right? So that's what it means by the location and direction, okay, that being reflected by the plane mirror, right? And the ray optic also permit us to determine the condition under which light is guided within a given medium, right? Example, glass fiber. So that one can be illustrated on the picture on the right hand side here. That is an example of fiber. That means the ray is being guided in the core, right? So that the ray will be going through the core and without any refraction outside of the core, right? And that is governed by the theta that's given here, the complement theta c, as well the theta c. All right. Let's look at the law of reflection, right? Mirrors are made of certain highly polished metallic surfaces or metallic or dielectric films deposited on substrates such as glass. Okay, the light reflects from mirror accordance with the law of reflection. Okay, so what that means is that reflected ray lies in the plane of incidence, right? The angle of reflection equals to the angle of incidence. Theta I equals to theta. Let's look at the picture here at the bottom, right, on the left hand side. We can see that a mirror, this is a mirror, and then there is a plane of incidence. So the ray into the plane of incidence is get reflected, right? So what the reflection law stating is that the angle of the reflected ray is equal to the angle of incident. Okay, and another view we can look into this on the right hand side here, that there's a mirror on the bottom and the plane perpendicular to that, right? We can see that the incident ray get reflected, right? So the reflected ray, the angle is equals to the incident ray. All right. Next, let's look into the law of refraction. Also, it is known as Snell's law. Okay, reflection and refraction at the boundary between two media of refractive indexes, which is known N1 and N2. And the incident ray is split into two. One is reflected ray, another one is refracted. So refracted also known as transmitted ray. Okay. General rule of thumb: reflected ray obeys law of reflection, and refracted ray obeys the law of refraction. Refracted ray lies in the plane of incident, okay, where the angle of refraction theta 2 is related to the angle of incident by Snell's law, which is given by N1 sine theta 1 equals to N2 sine theta 2. Let's look at the picture here on the left hand side. So we can see that there is plane of incident, right? And then the incident ray getting to the plane of incident, and then it's get reflected ray. So that is theta 1, where the theta 1 must be equal to theta incident, right? And then there is a ray get refracted or transmitted through, right? That is given by theta 2. So in order to find the angle of this theta 2, we can use the Snell's law equation, which is N1 sine theta 1 equals to N2 and sine theta 2. And N1 and N2 nothing but is the indexes for the medium, right? So here on the right hand side, we can see that the medium used is the air, which is N1 equals to 1, and water is N2 equals to 1.33. So by having this information, we should be able to get this theta 2 angle, okay, for the refracted ray. All right. Next one, optical components. Okay, one of the components of planar mirrors, right? It is actually reflect rays originating from from a point P1 here in the diagram, point P1, it gets reflected. And at the same time, we can say that the reflected rays appear to originate from the point P2 here. Okay, so that called as image, right? It is a virtual image. And the distance from P1 to the mirror and from the mirror to P2 is the same. Right? That is shown in the next picture here, right? It is an equal distance. Next one is a paraboloidal mirrors, right? Paraboloidal mirrors. The surface of the paraboloidal mirror is a paraboloid of revolution. It has the useful property of focusing all the incident rays parallel to its axis into a single point called the focus. All right. So if you look at the picture here, so all the rays are parallel to the axis, right, to the mirror, right? And this called focus. And the distance of PF is actually defined by the F here. That also called as a focal length. Next one is transfer matrix. All right, a ray is described by its position and its angle with respect to the optical axis. Okay, these variables are altered as the ray travels through the system. Okay, in the paraxial approximation, the position and angle at the input and output planes of an optical system are related by two linear algebraic equations. Okay, and the optical system is described by a 2x2 matrix called the ray transfer matrix. Right. Let's look at the picture here. The figure here. We have the input y1 theta 1 go through the optical system, and then we expect output to be y2 theta 2. Right. Y1 theta 1 is given in the y-axis and z-axis. Z-axis is the optical axis, right? So we have the theta 1 angle for the y1 at the input plane, and also we have the theta 2, expected theta 2 from the output plane, right? So from here we can derive an equation, the linear equation, y2 equals to ay1 plus b theta 1, and theta 2 equal to c y1 plus d theta 1. Right. So this equation A, B, C, D are real numbers, right, from equation 1 and 2. It also can be written in matrix form, right, where we can choose matrix M, right, that has all the elements A, B, C, D and characterize the optical system completely, right? That means y2 theta 2 to be determined by for any y1 theta 1. All right, and this is what is known as transfer matrix. So we look at the figure on the left, we can see that y2 theta 2 equal to A, B, C, D, which is the transfer matrix, and y1 theta 1, right? So we can solve this and we can derive the equation that we have, equation 1 and equation 2. Next one is fiber optic. Let's look into the inventor, Charles Cow, who was the awarded Nobel Prize in Physics 2009 for groundbreaking achievement concerning the transmission of light in fiber for optical communication. Right. Basic of fiber optics. It is an optical fiber is a cylindrical waveguide made of low loss materials such as silica glass. Okay. It has central core in which the light is guided, embedded in an outer cladding of slightly lower refractive index. Right? So what that means is that the cladding refractive index is lower than the core reflective index. Light rays incident on the core cladding boundary at the angle greater than the critical angle undergo total internal reflection and guided through the core without refraction. So here the critical angle, right, an angle which the boundary angle greater than the critical angle, then all the reflection will go through the core without any ray gets refracted into the cladding. Okay, and it also a remarkable technology in fabrication of optical fiber that allow light to be guided through 1 kilometer of glass fiber as low as 0.15 dB per kilometer. And due to this low loss that achieved by optical fiber, it already long ago replaced the copper cable for data communication. Okay. Some notes here, the A is actually referring to the radius of the core as well. The B is referring to the radius of the cladding. Right? right? And the material used for the cladding and the core is a combination of silicon dioxide and germanium dioxide. For the cladding is silicon dioxide. All right. Next one is numerical aperture, right? Based on Snell's law, is an equation that relates the angle of the incident light and the angle of refracted transmitted light at the surface of two different mediums, right? Which is given by n1 sine theta 1 equals to n2 sine theta 2. Okay. And the extension of Snell's law is the concept of total internal reflection and the critical angle. Okay. For any medium, there is an angle for which refracted light will be perpendicular to the normal, which is given here on this diagram that any refracted light, right, it will be perpendicular to the normal light. Okay. The critical angle, right, the critical angle here, n1 sine 1 theta 1 equals to n2 sine theta 2, where we can find the critical angle theta c by anti sine n1 divided by n2. Okay. If the incident angle theta 1 is greater than the critical angle theta c, the light will be completely reflected into the medium, right? There will be no any refraction. Okay. Right. Internal reflection and total internal reflection. Right. Internal reflection for n1 greater than n2. If the incident ray in a medium of a higher refractive index theta 2 greater than theta 1, and the refracted ray bends toward the boundary. When the angle are small, the relation between theta 2 and theta 1 is linear, that given by n1 sine theta 1 equals to n2 sine theta 2. Okay. As of total reflection, internal reflection, as theta 1 increases, okay, as theta 1 increases, theta 2 will reach 90 degrees first. Okay, this occur when theta 1 equals to theta c. Theta c is critical angle. Okay, with n1 sine theta c equals to n2 sine pi over 2, where when theta 2 is already reaches 90c, then the sine pi 2 will become 1, right? So that will give n1 sine theta c equals to n2. Okay. So from here we should be able to get the critical angle by taking anti-sine n1 divided by n2. Okay. When theta 1 greater than theta c, Snell's law cannot be satisfied and refraction does not occur. Okay. So the incident ray is totally refracted as it is as if the surface were a perfect mirror. Numerical aperture. If the Snell's law applied at the air core boundary, the angle theta A in the corresponding to the complement of theta C, right? Angle in the core is obtained. 1 times sine time theta A equals to n1 sine complement theta C. So this will give the sine theta A equals to n1 square root of 1 minus cos squared complement theta C. Also, this will be given the square root of n1 squared minus n2 squared. Okay. The acceptable angle of the fiber is therefore theta A equals to anti-sine of NA. Right. Theta A is actually to determine the cone, right, of the external rays that guided by fiber. Okay, that's the theta A. Where the numerical aperture NA is actually given by the n1 squared minus square root n1 squared minus n square root. NA is given square root of n1 squared minus n2 squared. So the numerical aperture here is describe the light gathering capacity of the fiber as shown in figure below. Light rays within the acceptance cone are guided by total internal reflection. The acceptance angle is crucial design parameter for coupling light into and out of the fiber. So from here, the accepted angle is critical to ensure the ray is guided through in the core, so that there is no any refraction. Okay. Right. Absorption spectroscopy. Okay. Absorption spectroscopy is a method that uses the wavelength dependent absorption, right, characteristic of material to identify and quantify the specific substance. Let's look at this picture here. So we have incident radiation P0 go through a sample, and then we have a transmitted radiation P. right? So from here we can see the energy level, right? Absorption. The energy level will move from absorb from 0 to energy level 1, correspond to the wavelength, right? So wavelength 1, or yeah, wavelength 1, and that will give us energy 1, right? At this, and also the energy 0 will move to absorb to energy level 2. That will correspond to the energy level 2 with corresponding to the wavelength 2. So what we can correlate here, the energy level is inverse proportional to the wavelength, right? So for higher wavelength, the energy level will be lower, and for the lower wavelength, the energy level will be high. Okay. Optical waveguide. Optical waveguide is a light conduit consisting of slab, strip, or cylinder of dielectrical material embedded in another dielectrical material of lower refractive index. The light is transported through the inner medium without radiating into a surrounding medium. So we can see the picture here, that the slab. So we can see the dark blue here. That's where the ray will be transmitting, right, or transporting. Right? So strip will be here, and the cylindrical here. This is an example of fiber that the ray will be transferred through the cup. Okay. John Tyndall is the first one to demonstrate the total interreflection, and he formed the basis of the guided wave optics. Let's look into a single and multimode fiber. Right? Geometry, refractive index profile, typical ray in a step index multimode fiber, a single mode fiber, and a graded index multimode fiber. Okay. Fiber with a constant refractive indexes in the core and the cladding are known as step index fiber. That's shown here, the step index fiber, where it has the constant refractive index for core as well as the cladding. Okay. When the core diameter is small, only single mode is supported, and it is called a single mode fiber. Okay. When the fiber with a large core diameter, then it will become a multi-mode fiber. However, the side impact to that is it will result in a modal dispersion, right? But the modal dispersion also can be reduced by grading the refractive index of the fiber core from a maximum value at its center to a minimum value at the core cladding boundary. The fiber called graded index fiber or grading fiber. Fiber V parameters. Okay, V is an important parameter that governs the number of modes of the fiber and their propagation constant. It is called the fiber parameter or the V parameter. It is directly proportionate to the radius to the wavelength ratio A over wavelength, right? And the numerical aperture NA. The number of TEM modes in planar dielectric waveguide is decided by V parameter. V parameter is given by 2 pi A over wavelength and multiply by the numerical aperture NA. Right? So the value that we get from V will decide whether it is a single mode or multi. So any value is below 2.4, then it is for single mode fiber. Any value is above 2.4, then we regard that as multi-mode fiber. And the NA we should be able to compute using this formula, which is N1 squared minus N2 squared. Square root N1 squared minus N2 squared. Okay. Some of the ray optic application in fiber optic communication, in fiber optic sensor, as well medical and healthcare. Next, let's look into the wave optics. Okay. Wave optic, Christian Huygens, right, advances several new concepts concerning the propagation of light waves. Thomas Young championed the wave theory of light and discovered the principle of optical interference, right, and defined light travel as wave. Okay. Wave optics, the wave theory of light encompasses of ray theory, as shown in figure below. That means wave will encompass the ray optics. The ray optic is the limit of wave optic when the wavelength is infinitely short. Okay. The ray optic theory to be useful as long as the light wave propagates through and around object whose dimension are much greater than the wavelength, which is d greater than the wavelength. The wave optic theory to be useful when the light wave propagate through and around the objects whose dimension are close to the wavelength, d equals to wavelength. The optical frequency and wavelength. Light propagates in the form of waves. Right? In free space, light wave travel with a constant speed of light, which is 3 by 10 power to the 8 meter per second. Right? So here in this the band diagram here, what we can see that the energy is given by h times v, where it also can be written hc over wavelength, where the lambda is given c over v here, right? So as the wavelength increases, the energy is reduces, and then as the wavelength reduces, the energy will be increases. All right. Next one is optical frequency at wavelength, right? As shown in figure below here, right? The range of optical wavelength contains 3 regions. One is infrared, which is it starts from 0.76 to 330 micrometer. That's infrared region, and then the visible region in the center here, visible region, that is taking from 390 to 760 nanometer. Right, and the ultraviolet region, which is shown in the pink color here, that is start from the 10 to 300 10 nanometer to 300 nanometer range. Right? The corresponding range of optical frequency stretches from 1 terahertz in the far infrared to 3 by 10 power to the 16 hertz in the extreme ultraviolet. Wave equation. Light propagate in the form of wave. In the free space, the light wave travel with the speed of c0. Okay. A homogeneous transparent medium such as glass is characterized by a single constant refractive index n, which is greater or equals to 1. In a medium of a refractive index n, light wave travel with a reduced speed. An optical wave is described mathematically by real function of position r, right, which equal to x, y, z, and the time t denoted by u r over r comma t, and this is known as wave function. It satisfies partial differential equation called the wave equation. Right. So here we can see that the wavelength or lambda naught is actually between one wave to another, and also we can derive the formula lambda equals to c over v, and the speed, right, or the velocity we can derive using a c naught over the index. Okay, and on this one is actually showing the wave equation, where the lambda is actually a start of the amplitude of the first wave until the start of the second wave. Monochromatic wave. Monochromatic wave is represented by a wave function with a harmonic time dependence. Amplitude and phase are generally position dependent, but the wave function is a harmonic function of time with frequency v at all positions. Okay, optical wave have a frequency that lie in the range of 3 times 10 power to the 11 to 3 times 10 to the power 16 hertz. And the optical intensity of monochromatic wave is the absolute square of its complex amplitude. The intensity of the monochrome wave does not vary by time. Right? So referring to the picture here on the left is a representation of a monochromatic wave of a fixed position r. Okay, where the wave function ut is a harmonic function of the time, right? Where the t is equal to 1 over v, right? And the b is a complex amplitude u, okay, where is given by a exponent j pi, okay, is a fixed phasor, right? And c is a complex wave function, right? Given by u exponent j 2 pi vt. It's a phasor rotating with the angular velocity, right? W equals to angular velocity given 2 pi v in radians, right? On the right hand side is the optical intensity of the monochromatic. What is given here is the square root of the amplitude u r squared is the square of a complex amplitude is the optical intensity. The optical intensity we should be able to compute by square this the complex amplitude. Okay. Reflection on wave optic. Reflection of a plane wave from a plane mirror, right? Phase matching at the surface of the mirror requires that the angle of incident and reflection be equal. Okay. Monochromatic wave propagates through media of different refractive indexes. Its frequency remain the same, but velocity, wavelength, and wave number are altered. Right? That's shown in this diagram, right? Where the wave the the wavelength is altered, right? Whereas the frequency remain the same. Okay, and the speed we can compute using the C naught over n, the index n, and also the wavelength. We should be able to get the wavelength naught divided by the index, as well the wave number. Refraction of a plane of wave at the dielectric boundary. As a monochromatic wave propagates through media of different refractive indexes, its frequency remains the same, but its velocity, wavelength, and wave number are altered. Okay, as given by this the waveform here that illustrated that the waveform, the velocity, wavelength, and the wave number are altered and can be derived using the formula here. Next one is diffraction of light. Okay, when an optical wave is transmitted through an aperture in an open screen and travels some distance in free space, its intensity distribution is called diffraction pattern. So that's shown here. The aperture here we have the dimension dx and dy. So when the light is traveled here, so that will be create a diffraction pattern. Okay, diffraction from the rectangular pattern, right? The central loop of the pattern has half angular width, which is given by theta x, right, equals to wavelength over dx, and theta y is given by wavelength over dy. Okay, so this optical wave transmission through aperture leads to a diffraction of light. Wave optic diffraction grating. Diffraction grating is an optical component that serves to periodically modulate the phase or amplitude of an incident wave. Okay, diffraction grating have found numerous applications as filters and spectroscopy. Okay. A diffraction grating is an optical component that serves to periodically modulate the phase or amplitude of an incident wave. It can be made a transparent plate with a periodically varying thickness or periodically graded refractive index. Repetitive array of diffracting elements include aperture, obstacles, absorption element can be used. Reflective diffraction grating is often fabricated from a periodically loose thin film of aluminium that has been evaporated onto a glass substrate. Interference. Okay, interference happens when the two or more optical waves are simultaneously present in the same region of space and time. The total waveform is a sum of the individual waveform. Okay, the basic principle of superposition follows the linearity of the wave equation. The phenomena of interference cannot be explained of the basis of ray optics, since it is dependent on the phase relationship between the superposed wave. Okay. Interferometer, right? An interferometer is an optical instrument, right, that split a wave into two waves using a beam splitter, delay them by unequal distances, redirect them using a mirror, recombine them using another beam splitter or spin, right, and detect the intensity of the superposition. position. There are three important interferometer. One is a Mach center interferometer that is shown here, Mach center, where it has a two mirror and a two beam splitter. So when the ray is being transmitted, it gets splitted here, and then it gets reflected through the mirror, and then it construct back on the other beam. Okay. The next one is Michelson interferometer, which is shown here B, that it has two mirror but one beam splitter, right? So what it does is that the ray will be split, and then it will be reflected by the mirror, and then again it will be split and then reflected by the mirror, and then it construct back. Okay. The third one is Photonic interferometer, where it has a three mirror and one beam filter, where the beam filter will split the ray and then reflected by the mirror, and the reflection also go on the two direction here, and then it will construct back that rays. Next, let's look into the electromagnetic optics. About electromagnetic optics, let's review about the inventor Maxwell. Right? He advanced the theory that light is an electromagnetic wave phenomena and defined light travel as electromagnetic wave. Okay. The fraction of light reflected or transmitted turns out to depend on the polarization of the incident light, which means that the light must be treated in the context of vector. So looking at this figure here, so the incident light now it will follow the polarized direction in the context of vector, right? So there is a polarizer. So polarizer will allow the light to travel whether in the x direction or y direction, follow the polarized direction or polarizer level. Theory of light. An electromagnetic field is described by two related vector fields that are function of position and time, also given by electrical field, right, and also magnetic field. Okay. These four equations are interrelated and satisfy the celebrated set of couple of partial differential equations known as Maxwell equation, which is the first one is Ampere law, that is the vector operator, right? Is using the vector operator as well the curl divergent and the curl operator. Okay. The V vector times H is the curl operator, right? We define the Ampere's laws, and the vector times electric is a Faraday's law, and also we have these the divergence, right, for electric as well for the magnetic. So that is defined by Gauss law, right? So here in this waveform, we can look into that the electric field is shown in the red color here, right? Red color form, and then the magnetic field is shown in the blue color form. Right? The wavelength is actually start of the wave, first wave amplitude until the second start of the second wave. Right? That's how we compute the wavelength. Okay, changing electric field, okay, it will generate the magnetic field, right? At the same, when we change the magnetic field, it will generate the electric field. Okay, next one is a wave equation. A necessary condition for electric and magnetic to satisfy Maxwell equation is that each of their components need to satisfy the wave equation. Okay, the wave equation may be derived from Maxwell equation by applying the curl operation. Right? The Maxwell equation and the wave equation are linear. The principle of superposition applies if two sets of electric and magnetic field are solution to those equations separately. Their sum also is a solution. Okay? So here we can use this the curl operation, right, which will give the wave equation under free space, and also the speed of light. We can use we can use the constant, which is 3 times 10 power to the 8 meter per second. three elementary solutions to Maxwell equation that are substantial importance in optics. Right? One is a plane wave. Then next is the spherical wave, Gaussian beam. Right? The medium is assumed to be linear, homogeneous, non-dispersive, and isotropic. And the waves are assumed to be monochromatic. Okay. The transverse electromagnetic or TEM plane wave, the monochromatic electromagnetic wave whose magnetic field and electric field complex amplitude vectors are plane wave with wave vector k that will be give HR equals to h naught exponent minus j k times r, where the k multiply h naught will give the omega the way the the w in e naught, as well the er, okay, e naught exponent to j k multiplied by r will give the k multiply the k number of vector k number multiplied by e naught will give w mu h naught, right? The complex envelope h naught and e naught are constant vector, right? And the k is equal to the n multiplied the k naught. N is referring to the refractive index. Okay. Let's look into the transverse electromagnetic TEM. E, H, K are mutually orthogonal from this figure here. E, H, K are orthogonal, right, as shown in the figure below. Since E and H lie in the plane normal, this is the plane normal, right, to the direction of the propagation of K. So then the wave is called transverse electromagnetic wave. Okay. The transverse electromagnetic wave, the vector E, H, and K are mutually orthogonal, right? The wave front surfaces of constant phase are normal to K. The ratio between the amplitude of the electric and the magnetic field is E naught over H naught, which is given by G mu or square root of mu of permeability. This quantity is known as the impedance of medium. Polarization of light. Okay, the polarization of light at the fixed position is determined by the time course of the electric field vector, which represent the direction of the electric field. Consider a monochromatic plane wave of frequency V and angular frequency equals to 2 pi V traveling in z direction with the velocity c. So the electric field lies in the xy plane and is generally described by by this real equation here, where the complex envelope will be A equals to AX x vector plus AY y vector. It's a vector with a complex component AX and AY, right? To describe the polarization of this wave, we trace the endpoint of the vector primitive Z by at the time t and at each position Z as a function of time, right? So the figure A here is the time course of the electrical field vector monochromatic light at several positions. A is the arbitrary wave, and the B is the plane wave or paraxial wave traveling in the Z direction. Okay. The matrix representation of a polarization devices, right? Consider the transmission of the plane wave of a arbitrary polarization through an optical system that maintain the plane wave nature of the wave, but alter its polarization. So in figure below. Okay. The complex envelope of two electric field component of the input incident wave A1x and A1y, okay, and output transmitted or reflected wave A2x and A2y are in general related by the weighted superposition. The structure of the Jones matrix T of a given optical system determines its effect on the polarization state and intensity of the wave. Okay, let's look at the figure here. The optical system input and this output, an optical system that alters the polarization of the plane. Okay, where the A2x is equal to T11 A1x plus T12 A1y, and A2y is equal to T21 and A1x plus T22 A11, where T11, T12, T22 are a constant describing the device. Okay, and also we can write this equation into matrix form. A2x, A2y equals to T11, T12, T21, T22, which is the matrix T matrix, multiply with this A1x and A1y. If the input and output wave are described by the Jones vector J1 and J2 respectively, then we can write the equation in the compact matrix form like J2 equals to T J1. That means the output is equal to the T matrix T multiplied with J1. Okay, the matrix T called the Jones matrix describe the optical system, whereas the vector J1 and J2 describe the input and the output waves. All right. Type of polarization, right? The first one is the linear polarization. The line in the polarizer represents the field direction that is permitted to pass. So which direction that we want to get the ray to be transmitted, right? Whether it's x direction or y direction. So the line will permit the direction of the ray. Okay. Next one is wave retarder, right? Wave retarder is optical device that alter the polarization state of the light wave traveling through it. That means the wave, we can have a off wave or quarter wave retarder. That means based on that, the optical will alter the polarization state, and that will decide the light wave traveling through it. Okay. Next one is a rotator. Rotator is a while wave retarder can transform a wave with one form of polarization into another. Rotator always maintain the linear polarization of the wave, but rotate the plane of the polarization by a particular angle. So in this case, the the retarder will remain the same, no change, but the changes will happen on the plane. So the plane will be rotated into a certain angle to allow the ray to pass through it. What is the importance of the polarizers, right? Polarization play a key role in the interaction of light with matter. First one is amount of light reflected at the boundary between two materials depend on the polarization of the incident wave. Okay. Amount of light absorbed by certain materials is polarization dependent. Right. Light scattering from matter is generally polarized sensitive. Refractive index of anisotropic materials depend on the polarization. Wave at different polarization travel at different velocities and undergo different phase shifts. So the polarization is modified as the wave advances. This property is used in the design of many optical devices. Polarization of plane of linearly polarized light is rotated by passage through a certain media, including optically active, liquid crystal, and certain substances in the presence of an external magnetic field. Now let's look into the quantum optics. Okay, about quantum optics, we have to start with Max Planck, right, who have suggested that that emission and absorption of light matters take the form of quanta of energy. Right. They also mentioned light emission or absorption is quantized. Okay. Whereas Einstein advances the hypothesis of light itself comprises of quanta of energy. So light comprises of quanta of energy, or it is regarded as a photon. Overview of quantum optics. Quantum optics deal with the optical phenomena that can only explain by treating light as a stream of photons rather than an electromagnetic wave. Okay. They are a progressive development of theory of light, namely start from ray optic, wave optic, electromagnetic optic, and then now we are into the quantum optic. Three general approaches can be clearly identified. One is a classical theory, Next is semi-classical theory, and then third one is quantum theory. And this is being summarized in table 1.0. So model classical theory, the atom is regarded as Hertzian dipoles, and the light is treated as a wave. Whereas in a semi-classical theory, atom is quantized, right? The light is treated as a wave. Okay. When you come to quantum, right, the atom is quantized, but the light is treated as a photon. Right? So three different theories used to model the interaction between light and matter. Okay. In classical physics, the light is conceived as electromagnetic wave, but in quantum optics, the quantum nature of the light is included by treating light as a photon. Electromagnetic optic provided the most complete treatment of light at confine of a classical optic. However, as we discussed, certain optical phenomena like are characteristically to quantum mechanical in nature that cannot be explained, like absorption, emission, photoelectric effect. Okay. These phenomena described by quantum version of electromagnetic theory known as quantum electrodynamics and also referred as quantum optics. The theory of quantum optics provide an explanation for virtually all quantum optical phenomena. And the quantum electromagnetic theory or quantum electrodynamics QED or quantum optics accepted as a theory that is useful for explaining almost all known optical phenomena. Let's look into photon. In quantum perspective, light consists of particles called photons. A photon carries electromagnetic energy and momentum, as well angular momentum or spin, that associated with its polarization properties, and it can also carry orbital angular momentum. The photon has zero rest mass and travel at the speed of light in vacuum. Max Planck notion of the photon initially grew out of an attempt by Max Planck in 1990 to resolve long-standing riddle concerning the spectrum of black body radiation. This has been achieved by quantizing the allowed energy values for each electromagnetic modes in a cavity from which radiation emanating. However, Albert Einstein extended the notion of quantization by considering the light itself to be a collection of photons, and this helped to explain the photoelectric effect. Okay, the picture here, the left one is showing the black body radiation spectrum, and then the right one is showing the photoelectric effect. All right. Photon energy, light propagates in the form of wave. In a free space, the travel speed is denoted by c equals to 3 times 10 power to the 8. The energy is E equals to hv, where h is the Max Planck constant, right? And v is the velocity. And also it can be written as the E equal to hc over wavelength, where wavelength is given as a c over v. The photon energy, right, provide energy of an electromagnetic mode is quantized to discrete levels, which is separated by the energy of photon, which is referred to the figure below here. And the energy of photon in mode of frequency v is given E equals to hv, where lambda is given as a c over v, and the photon energy where h is a Max Planck constant, which is 6.63 times 10 power to the minus 34 J per second. Okay. So there are three modes of different frequency and direction in cubic resonator. That's A. That's A here, mode 1, mode 2, mode 3. And B is allow energy in three mode of frequency, V1, V2, V3. So B here is a mode 1. We will be getting the energy following the V1 velocity, right? So V1 velocity will be reflect to the lambda 1. And then mode 2 will be going into the V2, right? When it transfer from one level of energy to another level. Okay, and mode 3 will be using the velocity of V3. The photon energy is given E equals to hv, which is equals to 1.99 times 10 minus 19 joule, and we can compute the the joule into electron volt by dividing this to 1.6 times 10 to the power minus 19 evolt. That will give us the photon energy equals to 1.24 evolt, okay, electron volts. This is the same as the kinetic energy imparted to an electron when it accelerates through a potential differences of 1.24 volt. The conversion formula between wavelength in micrometer and also photon energy is given as E equals to 1.24 over wavelength naught, but the wavelength naught need to be in the micrometer range. Okay. Interaction of photons with atoms, right? Based on atomic theory, an atom may emit or absorb a photon by undergoing downward or upward transition between its energy level, conserving energy in the process. The law governing these processes are described in quantum optics. Consider energy levels E1 and E2 of an atom placed in optical resonator of volume V, then sustain a number of electromagnetic modes. Interaction between the atoms and photon of a prescribed radiation mode of a frequency V equals to V naught, where h V naught equals to energy level 2 minus energy level 1. Since the photon of this energy match the atomic energy level difference. Three forms of interaction are possible. One is absorption, next is spontaneous emission, and stimulated emission. Let's look into the absorption. Absorption, the mechanism of absorption, if the electron in an atom is initially in the lower region, referring to this figure, if the atom is in the lower region or electron is in the lower region, okay, and the radiation mode contains a photon, okay, the photon may be absorbed, okay, the photon may be absorbed, and the electron in an atom raised to the upper energy level, which is level 2. Okay, this process, which induced by the photon, okay, and is called absorption. Okay, it can only occur when the mode contains photon. Okay, so referring to this figure, absorption of photon energy HV leads to an upward transition of an electron in an atom from energy level 1 to energy level 2. The next one is spontaneous emission. If the electron in an atom is initially in the upper energy level, it may decay spontaneously to the lower level energy and release its energy in the form of photon, referring to the figure here, right? The photon energy is added to the energy of the electromagnetic mode. This process is called spontaneous emission because the transition is independent of the number of photons that may already in the mode. Okay. So spontaneous emission of the photon into a mode of frequency V by an atom transition from energy level 2 to energy level 1. The photon energy level now is given by energy level 2 minus energy level 1. Next one is stimulated emission. If the electron in an atom is initially in the upper level energy level, right, and the radiation mode contains a photon, the electron may be induced to emit another photon in the same mode. It will have another photon in the same mode. This process called as stimulated emission. The presence of a photon in a mode of specified frequency, propagation direction, and the polarization stimulate the emission of duplicate is called a clone photon, with precisely the same characteristic as the original. So it will have the same energy level. Okay. The photon amplification process is a phenomena that underlies the operation of laser amplifier and laser. Okay. So here the figure stimulated emission is a process whereby a photon energy HV stimulate the electron in the atom to emit a clone photon as it's undergo a downward transition. Okay. Next one is fluorescent spectroscopy. Fluorescence is the phenomena that the material emits light at one wavelength when you eliminate it another wavelength. A fluorescent material is called a fluorophore, and sometimes fluorescent dyes or labeling regions or strings. Right. So here we know the energy level is equals to 1.24 divided by the wavelength in micrometer. So here the fluorophore will absorb light at the lower wavelength, right? and then the process is also called excitation, and also the light will be emitted at the longer wavelength. Right. Let's look into this natural fluorophores. Right. These two chlorophyll A and B here. A and B, which is shown in the green color, is the chlorophyll A with the 665 nanometer, and also chlorophyll B is given in the blue color, which is 565 nanometer. Right. So here is that we have the color and wavelength, and then the light is being reflected on the leaf, which is the green, with 495 to 570 nanometer wavelength. So what will happen is that it will absorb the red and blue wavelength, right, and allow the green wavelength to be passed through, right, and the fluorescence is in the red wavelength. Next, let's look into the laser, right? Laser is light amplification by stimulated emission of radiation, right? Towns, Basov, and Prokhorov developed the principle of light amplification by stimulated emission and radiation, which is called laser. They received the Nobel Prize for this work in 1964. What is the working mechanism of laser? Laser is a device that emits lights through a process of optical amplification based on stimulated emission of electromagnetic radiation. Right. So we can see that here the stimulated emission is that it will be generating another photon with the same energy level, right? Or we call it a clone photon. Right. Some of the components that needed for the laser is a gain medium, laser pumping energy, high reflector, output coupler, as well the laser beam. Laser and optical oscillator, it comprises a resonant optical amplifier whose output is feedback to the input with a matching phase. So we can look in this figure here, there is op-amp here, the amplifier, and the output is being feedback to the input. Okay. The increase of the signal is ultimately limited by saturation of the amplifier gain, and the system reaches a steady state in which an output signal is created at the frequency of the resonant amplifier. Okay. A laser consists of an optical amplifier, which is comprising an active medium, placed within an optical resonator. The output is extracted through a partially transmitting mirror. Next one is LED, right? LED is a light emitting diode. It's just like a normal PN junction diode, but with light emitting properties. LED operates in a forward bias. The N-type semiconductor is heavily doped than the P-type, forming a PN junction. Forward bias, operate in forward bias, the potential barrier gets reduced and the electron combined at the depletion layer or active layer, and the light or photon emitted or radiated in all directions. So the forward bias connection is that the positive terminal will be connected to the P-type and the negative terminal will connect to the N-type. And at the barrier, right, the barrier, there will be, when it's forward bias, there will be a combination of the electron as well holes that will generate the energy. Semiconductor photon sources, okay, light emitted from semiconductor material as a result of electron hole recombination. Okay. External source of energy can be used to produce electron hole pairs in sufficient number such that they produce large amount of spontaneous recombination radiation, causing material to glow or luminance. Right. This can be achieved by forward bias of PN junction. LED forward bias PN junction fabricated from direct bandgap material that emits light via injection elimination, which is referred to the figure A here. Junction region may then be used as semiconductor optical amplifier, figure B, right, with the appropriate feedback, which is referring to laser diode in figures. Semiconductor photon source in the form of LED or laser diode serve highly efficient electron to photonic transducer. Forward bias semiconductor PN junction diode operate as an LED, and B is the semiconductor optical amplifier, and the C is the laser diode. Photodetector being discovered, Heinrich Hertz discovered the photoelectric effect in 1987, and its origin was explained by Einstein Einstein in 1905, where Einstein advances the hypothesis the light itself comprises a quanta of energy. For Sean, he developed the fundamental of probability distribution that describe a photodetector. Photodetector. Photodetector is a device that measures photon flux or optical power by converting the energy of the absorbed photon into measurable form. Two principal classes of photodetector are in common use: photoelectric detector and photothermal detector. Operation of the photoelectric detector is based on photoelectric effect, is known as photo effect. Absorption of photon by material causes electron to transition to higher energy level, resulting in the mobile charge carriers. Under the effect of an electric field, this carrier move and produce measurable electric current. Photo effect takes two forms, external and internal. Photodiode, it has two. One is a PN and then PIN junction. The photodiode is based on a simplified PN and or PIN junction. In the case of PN junction diode, carrier are generated in the depletion region. The disadvantage of PN junction photodiode is the depletion width is small and deep, depends on the doping concentration on the semiconductor. However, this can be overcome by using a PIN junction photodiode, which is a special case of PN junction photodiode. Advantage of PIN photodiode over PN photodiode. PIN diode is an PN junction with an intrinsic layer sandwiched between the PN and diode. Okay, that's shown here. There is intrinsic layer between the PN. Right. Energy band diagram, charge distribution, and electrical field distribution for reverse bias PIN diode are illustrated in the figure here. Increasing the width of the depletion layer of the device where the generated carrier can be transported by drift. Increase the area available for capturing light. The advantage of a PIN structure is that the quantum efficiency, sensitivity, and gain of the device can be controlled by thickness of the intrinsic region, right? While a thin P and N region can be maintained. Okay? So the figure here is showing the PIN photodiode structure, energy band, charge distribution, and electrical field distribution. Advantage of photodetector, the sensitivity, maximum output photocurrent at the given input photon or optical power. Efficiency, efficient conversion from photon to electron. Response time, very fast response to operate at a high frequency. Signal to noise ratio is low noise for reduced error, and it has high reliability as well as low cost. Okay. The application for quantum optic camera is mainly have both the PN junction as the PIN junction. The art of any camera is optical sensor. Modern sensors are solid state of electronic devices containing up to millions of discrete photodetector site called pixel. At present, almost all sensor in machine version fall into one of two categories. One is a charge coupled device (OCD) or complementary metal oxide semiconductor images. Next one is the modulator. Okay, modulator is an optical modulator is a device which is used to modulate the intensity, the phase, wavelength, and also the polarization of the light beam. Okay, light photons, it can modulate the phase, amplitude, position, time, wavelength, as well as polarization. Right. The family tree of optical modulator has absorptive modulator as well as refractive modulator. Whereas on the refractive modulator, there is electro-optic modulator and also acoustic optic modulator. For electro-optic modulator, they are phase modulator, amplitude modulator, and polarization. All right, that's conclude my presentation on introduction to photonic. As a reference, I need to give an acknowledgement that this presentation was taken or cited from the lecture notes from Dr. Sivananju. As well, some notes was taken from the fundamental of photonic third editions. Okay, thank you.